In this video, we're going to start to cover section 6-7. This is the last section in chapter 6, and it just ties a lot of stuff together and brings it to some real life applications or coming up with models that will model real life situations. And in this video, we're going to do real life problems that involve right triangles. The next video, 6-7 day 2, we'll talk about directional bearings for sea and land navigation. And the day 3 video will cover real life problems with harmonic motion. So some of this section here is going to be a little review, in applications involving right triangles. In this section, 3 angles of a right triangle are denoted by the letters A, B, and C, where C is always the right angle. The lengths of the sides opposite these angles are lowercase a, b, and c, where c is the hypotenuse, which of course is across from the right angle. And we did something like this a few sections ago when we solved right triangles. So in example 1, we're going to solve the right triangle shown in the figure, find all unknown sides and angles. So we're given one side and one of the acute angles. And I think the easiest thing to find is the missing acute angle. In this case, it's angle B. And since it's a right triangle, we have one right angle. The other 2 angles add up to 90. So angle B is going to be 90 degrees minus angle A, or 34.2 degrees. If we subtract those, we find that angle B is 55.8 degrees. So there's our missing angle B. Now we got to find the missing sides A and C. Well, let's see. I'm going to go from angle A, and from angle A here, if I want to find side A, that is the opposite side, and the side that we know is the adjacent side. So I ask myself, what trig function deals with opposite and adjacent? Well, that's got to be tangent. The tangent of an angle is equal to the opposite side, in this case it's A, and the adjacent side is B. So let's fill in there what we do know. We know that angle A is 34.2 degrees, and that's equal to A divided by B, and B we know is 19.4. And if we solve this for A, we would multiply both sides by 19.4. We're going to get A equals 19.4 times the tangent of 34.2 degrees. And here, we would make sure our calculator is in degree mode. We'd plug in 34.2, take the tangent of that number, and then multiply that by 19.4, and we get approximately 13.8. So side A here is 13.8. And now we can solve for C, the missing hypotenuse. We could do Pythagorean theorem, 19.4 squared plus 13.8 squared would equal C squared, or we could set up another trig function. I'm going to set up a trig function. Let's see. Here again, we know this angle is 34.2. We know the adjacent side, and we want to find the hypotenuse. So what trig function deals with adjacent and hypotenuse? That's cosine. The cosine of angle A, or let's just make that right now the 34.2 degrees. The cosine of the angle is equal to adjacent, 19.4, divided by the hypotenuse C. So to solve this for C, we would multiply both sides by C and then divide by the cos of 34.2. And what we're going to get is C equals 19.4 divided by the cosine of 34.2. To punch this in the calculator, I would do 19.4 and then divided by 34.2, hit the cosine key, and then equals, and we get approximately 23.46. And there's every missing side, and every missing angle has been accounted for. Again, that's kind of a review. In an earlier section, we did solve for right triangles. So let's do something similar with more of a real-world application. There's a safety regulation that states that the maximum angle of elevation for a rescue ladder is 72 degrees. A fire department's longest ladder is 110 feet. What is the maximum safe rescue height that we can use this ladder for? So here we have our picture. And sometimes those pictures can get a little cluttered. I like to break them down into the bare essentials. So let's see here. I'm going to orient this picture, or the right triangle, sort of like what we see in the picture. Here we know this angle is 72 degrees. That's our maximum safe angle, 72. The length of the ladder, which is the hypotenuse of this triangle, is 110 feet. Here is our right angle. And they're asking us to find the maximum safe rescue height, which is going to be this opposite side. Here they're using an A for it. So we want to find this side A. So I can get that picture out of the way. So let's see. Here is our given angle, 72 degrees. We want the opposite side. We have the hypotenuse. What trig function deals with opposite and hypotenuse? Well, that's the sine of the angle is equal to opposite over hypotenuse. And we do know the angle here is 72 degrees. Our opposite side is what we are looking for. Our hypotenuse is 110. So to solve for A, multiply both sides by 110. A equals 110 times the sine of 72 degrees. So here we just punch that into the calculator. 72, hit the sine key, multiply that answer by 110, and we get approximately 104.6 feet. Now, example 3 here is a little more complicated. At a point 200 feet from the base of a building. So here's our base of our building. A point 200 feet away is right over here. The angle of elevation to the bottom of a smokestack is 35 degrees. So here we have a 35-degree angle that takes us to the bottom of this smokestack. It's at the top of the building, the bottom of the smokestack. Whereas the angle of elevation to the top is 53 degrees. So here is a 53-degree angle. And if we follow that up, we take that to the top of the smokestack. Find the height of the smokestack alone. So let's see, what's the height of the smokestack by itself? Well, if we find the overall height of the total building and the smokestack, and subtract out just the height of the building, we'll be left with just the smokestack. So I'm going to come here under the picture, and we'll sort of scale this down and do it in chunks. So this will work here. If we want to find the height of both the building and the smokestack, we're going to use the 53-degree angle. Oops, 53 degrees. This bottom length of the triangle is 200 feet. That doesn't change. So to find this overall height, let's call it x. We want the opposite side. We have the adjacent side. So of course that's going to be tangent. The tangent of 53 degrees is equal to the opposite side x over the adjacent side 200. And let's see here, we'd multiply to solve for x, we'd multiply both sides by 200. Oh, and that's not degrees, that's feet. 200 times the tan of 53. And if we punch this in the calculator, 53 degrees tangent times 200, we get approximately 265.4. So here, we're going to get 265.4 feet. And again, that's the height of the smokestack and the building. So maybe here red will show up pretty good. This overall height is 265.4. We also were given the 35-degree angle. The smaller angle was 35 degrees, and that just took us to the height of the building. That stopped right here. So, our opposite side, let's use x again. This adjacent side is still 200 feet. So again, we're going to use tangent. We want the opposite. We have the adjacent. That's going to be tangent. the tangent of 35 degrees is x over 200. And again, multiply both sides by 200. X is 200 times the tangent of 35 degrees. And if we punch that in the calculator, we're going to get approximately 140 feet. So the height of just the building, why did I put degrees again? 140 feet. So the height of just the building is 140. So what's the height of just the smokestack? Well, see, the overall height was 265.4 minus the height of just the building, and we'll get the smokestack by itself. So if we subtract there, we're going to get 125.4 feet for just the smokestack. Example 4, in the first few, we were finding the length of a missing side. Here we're looking for a missing angle. A swimming pool, 20 meters long, 12 meters wide, which that isn't relevant to the problem. The bottom of the pool is slanted, so the water depth is 1.3 meters at the shallow depth, 1.3, and 4 meters at the deep end. So this overall length is 4. If we subtract the shallow 1.3 from 4, we get the depth here of the deeper end is 2.7 after we take into account that 1.3. Blah blah blah. Find the angle of depression to the bottom of the pool. So we are looking for, I'll use red here, this angle. And let's see, we have the side opposite the given angle, or the angle that we're looking for, and we have the side that is adjacent. Let's see here. If I redraw this with just the nitty-gritty that we're looking for, here's the angle that we want, theta. We know the distance across here is 20 meters, and we know just this piece is 2.7 meters. So we have the opposite side, we have the adjacent side. That means we have to use tangent. The tangent of angle theta is equal to opposite 2.7 over adjacent 20. Remember, we want to get theta by itself. How do we get rid of tangent? We use tan inverse. Tan and tan inverse will cross each other out. So we have theta equals the tan inverse of this fraction, 2.7 divided by 20. So on your calculator, divide the fraction. 2.7 divided by 20, you'll get a decimal. Take that decimal and perform the tan inverse operation. And we're going to get angle theta is approximately 7.69 degrees. All right. We got a couple huddle problems. For number 19, you're finding the length of this shadow. Basically, you're finding the adjacent side. In number 21, we're finding a missing height. We have a ladder leaning against a wall. Maximum angle is 80 degrees for the ladder. How high up the building will that ladder reach? So pause the video, try the two huddle problems, come back and check your answers. So let's check out this first one. So the sun is 25 degrees above the horizon. This is our 25-degree angle. Find the length of the shadow cast by a 100-foot building. So we're looking for this length. How long is that side? We know the height is 100. So we have our angle. We have the opposite side. We want the adjacent side. Opposite and adjacent means it must be tangent. The tangent of 25 degrees equals opposite is 100 over our adjacent side, let's call it x. And if we manipulate this and solve for x, we're going to get x equals 100 divided by the tangent of 25. So on the calculator, 100 divided by 25 tan equals, and we'll get approximately 214.45 feet. In the second problem, We're going to have to draw a little picture to go with it. Here's our building, and we have a ladder leaning against the wall. A 20-foot ladder. Well, that means this is 20 feet. Leans against the side of a house. Find the height of the top of the ladder to the ground if the angle is 80 degrees. So here's our 80-degree angle. We want to know how high up the building we're reaching. We'll call that x. So from our 80-degree angle, we want the opposite, and we have the hypotenuse. That means we have to use sine. The sine of the 80-degree angle is opposite x over hypotenuse 20. So if we solve for x, we're going to multiply both sides by 20. X equals 20 times the sine of 80 degrees. Well, 80 sine, and then we get that value, times 20. We're going to get x is approximately 19.7 feet. There we go. And the homework problems for this section, 6-7 day 1, page 526, 16, 18, 20, 21, and 22.